First of all, thank you very much for attending my presentation, and thank you also to all the organizers, and thank you for inviting me. So where am I now? I'm in Pau, so you can see here. It was when David contacted me to present something, I said it would be the interesting, let's say, event to present the Interluis project and to have more interactions. But actually, when I checked my dates, I was a couple of hours ago in Algeria, so I just arrived home less than an hour ago. So it was a bit difficult to come physically to Angers, and it's such a pity. But and then I saw that the hybrid mode could be the right places. So I said, okay, let's try to present something in the Connected Stick World Tour. I realized afterward that my work is not really on phenotyping, and somehow the connected stick is not connected neither. So I'm going to try to show you how the stick could be considered as connected, but I hope that the information that I'm going to give you will be useful anyway. So I did work on low-cost camera and connected autonomous camera, but this is not really the purpose or the focus of this talk here. But this is something that I still follow, and all the presentations that have been made beforehand are quite interesting, and I will follow them very carefully. So this project is more focused on the Mediterranean area, so it's a collaborative projects with 2 Moroccan partners and 2 Algerian partners. And of course, we are a number of European countries also. So we have 2 partners in France, and we have 1 partner in Germany and 1 partner in Greece. So I just want to say that it's a collaborative project trying to improve the knowledge on agriculture practices, especially on how to optimize aggregation. And so therefore, half of the partners are more on the agronomic side, and half of the partners are more on the computer science or ICT side. So I'm the coordinator of the project, and I'm more on the computer science side. So we focus on water resources, and maybe worldwide is going to be a big problem. It's already a big problem in many countries, and especially with the countries we are working with. They actually normally they are in a semi-arid, let's say, region, but they actually suffer from very arid situations. So the level of waters in the underground waters is I mean, dangerously low everywhere. And as you can see, I mean, they have, I mean, the whole region is subject to recurrent and persistent dryness. So this was the motivation for our work here. And we all know that smart agriculture is not a new subject, and you can see here an ideal smart agriculture scenarios where you have you could have sensors, of course, so smart agriculture with connected sensors. More global vision of smart agriculture involving a lot of advanced techniques such as satellite data and localization and control management of your own farm. So I try to show from quite basics connected agriculture to more global agriculture to what we could call connected or smart agriculture that could be managed from a tablet, for instance. The problem with this kind of scenario is we know it can be possible, but it costs a lot. So this scenario could be possible probably for big farms, but definitely for the audience for the, let's say, the farmers that we are targeting in Morocco and Algeria, definitely this kind of scenario is very difficult to implement because of a cost, mostly because of the cost issues, but also because of the complexity of the technology. So complexity, of course, is highly related to has a big impact on the cost. Cost for deployment, cost for maintenance, cost for having people taking care of the technologies and so on. It is actually always a trade-off. So in this graph, I also try to show that efficiency can be high, usually with high-end system. There's no doubt about this. We know how to improve. Most of the farmers we are working with, the small scale farms or smallholders farmers, they actually have a very low cost of the technological components. It can be very low or it can be completely zero because they are not deploying any technological. Some of them do have drip irrigation. Some of them, I mean, there's a large program for having more advanced irrigation techniques. But even if it's drip irrigation, they actually don't know really what are the conditions. Usually they base on the experience. They say, okay, let's try to irrigate 1 hour every 2 days. And if the plant sits okay, if it doesn't die or it doesn't see any kind of obvious diseases, then they will stick with this kind of scheme and they are not going to change because they believe that it's going to be good. So I'm not saying that it is not good, but maybe there's room for a lot of improvement. Maybe saving one irrigation cycle every 5 cycles, for instance, and then you can save at the end 20% of water. So what we want to do is to see what kind of research and innovation we can have, to bring low-cost sensing technologies to improve the irrigation holders. So irrigation with soil moisture sensing is not new. We know that we should deploy sensors and then we should analyze the data of the sensors and then based on the analysis decide when we have to irrigate. Okay, so and then we could start the irrigation manually or we could start, of course, automatically. Well, it is not as simple as it seems because, okay, we know how to deploy sensors. We know we have several types of sensors, but actually there are many technologies of sensors. Okay, and then regarding the analysis, it is also not that simple because if you're using low-cost sensors or lower-cost sensors, but even with high-end sensors, you need to take into account many parameters: soil characteristic, soil density, soil salinity, soil texture, soil type, whatever, and also maybe a lot of atmosphere or weather parameters such as evapotranspiration, soil, plant, atmosphere continuum, and so on. And then when you decide to irrigate, you actually have to take into account the irrigation type. Most of them have traditional gravity-based, mostly flooding in furrows, irrigation techniques. But even if they do have drip or sprinklers or other kind of control, not control, but more focused irrigation techniques, then we still have to take that into account because the impact or how the water will get into the soil can depend, of course, on the irrigation type. And also there's a lot of relation with the plant, the crop variety, when the plant is at its development phase, and of course the relationship with our agriculture inputs. So the project has 3 main objectives. First is to provide a low-cost system. So this is probably where I'm going to focus regarding the connected stick. And then the advanced technologies to analyze this data. So we're going to use advanced calibration of sensors. We're going to use advanced prediction, advanced analysis of data. And the third objective is because we're dealing with smallholders who has very, let's say, less technological background. Some of them, they don't even have a smartphone. Then what we want to have is a completely fully autonomous and plug and sense system. So at the beginning, we had this idea of, let's say, some kind of starter kit where inside this box, then you will have 1 device sensors and then 1 gateways in order to be able to analyze and take all the decisions. So the main target, of course, was the small-scale farms, the smallholder farmers, and many of them actually don't have internet at all. So this is why the connected stick is maybe a little bit, I mean, not exactly true, because we are not connected to the internet, or maybe we could be connected to the internet, but our choice was really to not be connected to internet in order to have everything embedded into the systems in order to be able to deploy them even without internet access. So we had this idea like 2 years ago, and now we do have the starter kit ready. I mean, more than 1 year now, and we are still in the deployment. We're discussing with smallholders in order to deploy the system, to get feedbacks from them in order to fill in. Or to understand a little bit better what should be improved regarding the interfaces, regarding the robustness of the various parts of our system. But I think that we have been quite successful. We have 2 versions of the soil sensors. We try to keep the cost as low as possible. So as you can see here, we have on the left a simple capacitive sensors. Capacitive because of the technology. We are measuring the volumetric water content around let's say the probe. So if the probe is placed close to the roots of the plant, then you can have pretty much the interpretation of how the soil close to the roots of the plant is. And then we have a more sophisticated tensiometer. So we're not designing the sensors itself, but we're using the watermark sensors from Aerometer. And this is water tension that measures let's say the force, needed to take water out of the porosity of the soil, and that try to mimic or interpret how the root system of the plant can take the available water. Okay, and in this case, the soil temperature is a very important parameter because it's going to impact on that kind of require water tension. So we usually have a soil temperature sensor with a tensiometer, which is not the case with the capacitive sensors. So you can see the prices here. It ranges from 30 euros to 60 euros only for the devices. And then, of course, we do have the gateways. And I'm going to talk about the gateways later on. So this is how I interpreted our IntelliRisk connected stick. One of the main objectives was really to have a very simple as possible design for the hardware platform. So as you can see, I believe it is hard to make it simpler. You have a microcontroller that you can buy for €1 in Chinese manufacturer. This is the Arduino Pro Mini. We take the 3.3 volt version in order to decrease the power consumption. We have the radio modules. We have a very simple PCB here that we design very quickly, and then we have some terminal blocks to connect sensors. So you actually see the results here. We added some kind of switches. We have some kind of cases here. So we have been deploying this kind of system, not this one, but this similar IoT system in many Africa countries for many years. So we validated each step of the casing in order to be waterproof, in order to be robust, in order to not, having problem with the high temperatures and so on. So this is the connected stick. We have one, they are in my garden actually, this one. It's easier for me to maintain, to test them and to make any changes it requires. But we also have, of course, this kind of stick out in the piloting farms both in Morocco and Algeria. So as you can see, there's the capacitive sensor here, and here is the tensiometer with the tensiometer buried at about 30 or 40 centimeters, and then the soil temperature sensors. So connected stick, connected to what exactly? Because our stick is definitely not connected to the internet because of power consumption. So it's design choices. We didn't want our stick to be connected to the internet, but it is connected to a gateway. So the gateway will be placed in this smallholder office, for instance, or somewhere where it can be protected from the rain. We actually do have an outdoor gateway that can also be placed if there's no such possibility. But of course, we have to power the gateway somehow. So if we do have electricity, it's quite simple. But if we don't, then we need to install, a solar panel with batteries and so on. So nothing difficult, nothing new actually, but that adds a lot of complexity. And this complexity we just want to avoid right now because we are still in the process of trying to get feedbacks from the smallholders to see how they use the system, how they feel about the user interface and about the feedbacks provided by the devices, how this feedback helped them into interpreting the soil condition and maybe hopefully improve their irrigation practices and so on. So whenever the deployment is too difficult, then we maybe switch to another farm. And maybe if the range is too far, then maybe we just place our sensors to a closer field, to be in range with the gateway. So we try to simplify a little bit the piloting phase that we are doing right now. One of our priorities is to have the lowest power consumption possible. So we managed to have something like a below 5 microamp in deep sleep mode of the whole system. So we also choose to be able to power the entire system with just 2 regular alkaline batteries. We don't want, the big lithium-ion batteries or the 3. I mean, it's possible to have 3.6-volt battery, but these are more difficult to find. So the regular alkaline one, but of course we have to take the heavy duty or the long life, Duracell, Varta. I'm not doing any advertisement, but I usually say to my partner, please take a good quality batteries. And one way to know whether it is good quality or better quality, try to take it in your hand. If it's a little bit heavy, then it's probably a little bit more higher quality. So with this kind of battery, with 1 transmission every hour, we got over 2 years of operation, continuous operation. Okay, so when we talk about when we talk to smallholders, we know that they have cycles for the seeding, cycle for the harvesting, and so on. So usually they know that they have to switch off the sensors. So they have to deploy it, and they have to take it, and they have to switch off the sensors and for them to be ready for the next cycle. So usually for this kind of autonomy, it's possible to have maybe 3, 4, 5 harvesting cycles without any problem, without only 2 batteries. So this was our highest priority. And actually, depending on the plant, whether it is tomatoes and the region, because some smallholders can have like 2 harvesting for potatoes or for crops and so on, then of course the statistics regarding the sensor device that are deployed can be different, of course. So there comes some key to low-cost design that we took. So again, we really wanted a very simple design of the shell components in order to have very easy integration. So we have the list of all the materials, and we have links to where you can buy it. Of course, it's not mandatory. Again, it's not it's not commercial at all, but just for our partners to have a look at the hardware and to know which one they have to order. So easy integration in order to have a generic platform, in order to be easy adaptable, so that we can connect all the type of sensors. So this is something that is also one of our priority, because we don't want to reproduce the drawback of many commercial systems, which are usually high integration and also vendor locks in phenomenon, where actually they cannot change the technology. So we want to have a very generic platforms where the sensors could be connected, and all the parts could be easily maintained or changed eventually when there are some let's say a failure of some electronic parts. A large part of the project is on technology transfer, capacity building. So this design choices fits well our objectives. I'm not saying that it's going to fit all objectives of smart agriculture, but at least for this project, it's really fits well our objectives of involving local actors in order to be able, maybe hopefully in the future, to build a whole ecosystem regarding smarter agriculture in Morocco, Algeria. But of course, this kind of approach applies to many countries. We also investigate several low-cost design space. So the first one I already explained to you. We have a second one where actually we would like to add very simple solar panel support. Why low cost? I mean, it's a low cost support for solar panels, so it means that there's no complex hardware to manage the charging of batteries and so on. So a large part is done by software, which is more flexible. But then it puts some constraint on the choice of the battery technology. So maybe it could be contradictory with what I said previously. Our choice of using the most alkaline battery that you can find everywhere. But actually, when we talk with our partners, they say that having solar panel could really help in some cases. If we need to use more, let's say, demanding sensors, and also because we wanted a PCB where you're going to be able to connect it more easily, the various sensors. So I would say that this first version was something very generic. This first version is still generic, but it is more targeting the Intel RISC project, where you have terminal blocks for the sensors that we have been selected for the project. And also one of our partners, they also wanted to develop their own platform, less generic, but still generic enough because you can connect many type of sensors, and they wanted a more robust solar panel circuit. So of course it's going to cost a little bit more, but one advantage clearly is that it is possible to scale up. Why do we still find this approach very interesting? Is because everything is open source, and it's easy for us to say, okay, now we have more specialized sensors, so we actually change a little bit the schematic of the boards, not the core, but how the connectors are the layout, the wiring, and how the terminal blocks are placed in order to fit our let's say constraint. And then we make the production in China, and then we order 100 of them, and we can change very quickly from one project to another, or from one application to another. So this is something that we also like in the project. Regarding the accuracy, if you're using low-cost sensors, of course, you have to worry about that, because we don't want to deploy something low-cost, but so low that you actually can do anything with that. So we want low-cost in the design and in the choice of the various hardware components, but we also want to be able to provide valuable feedbacks. So our various partners are conducting extensive calibration tests for the capacitive one, for the tensiometer one. So we compare to let's say the system provided with the manufacturer. So we integrated many equations, many corrective and predictive, let's say, mechanism. We also wanted to test in a large range of conditions in order to be able to assess on the impact of external noises, solar radiation on the sensor, on the, let's say, brown part of the sensors, things like this. So we try to incorporate as much as possible in order, again, to improve the accuracy of the local system. I just want to say some words about the autonomy of our system. I tried to give some insight. What we wanted to do is really have something like a plug and sense, you know. So the smallholder receives a box with a starter kit, and then he deploys the sensor, he switches on the gateway, and then he's done. Okay, so this is what we wanted to have. So we work a lot on the interface of the low-cost gateway. So this is a Raspberry Pi. We have a small OLED connected, and all the information, all the important, let's say, all the important feedback could be visualized very quickly on the Raspberry, without the need to connect to the Raspberry or whatever using smartphone. But of course, if some smallholders, they feel comfortable with technology because they use smartphones and they're used to mobile applications, then we have an embedded web interface. So it is not a mobile application, it is more like a embedded web interface on the gateway. You use your smartphone to connect to the Wi-Fi, to the hotspot advertised by the gateway, and then you have a very good very nice responsive interfaces where you can have historical data and so on. We have been doing a lot of piloting, a lot of visits, a lot of discussions with smallholders. We are in the active phase of the deployment of the system in various farms in Algeria and Morocco. So we are compiling all these feedbacks, and hopefully we will be able to try to scale up to more farms. So currently we are working with, I would say 10 farms in Algeria, approximately 5 or 6 farms in Morocco. And near the end of the project, then we hope to be able to scale to, let's say, more than 20 farms to generalize a little bit, but we're still waiting to collect the first feedbacks. So how do we try to make it smarter?
Excuse me?
Yes, that's right. That's right. I have to stop. So let me go quickly. We just want to add the intelligence by having outside applications embedded on the gateway, and I think I can talk about the capacity building, because one of the main objectives of the project is to increase capacity buildings of local actors. And then if you want more, and then I directly jump to the question. Sorry for the time.
Okay.
Do you hear us?
Yes, I hear. Sorry, I hear you.
Sorry, but the time is running off.
Yeah. Sorry, I made a mistake. I kept checking the time, and I said, "Oh, okay, I have half an hour," but actually it was 20 plus 10. Sorry about that.
Directly. So perhaps time for a very short question. Online, Xavier? No?
Okay, thank you very much, Congduc. So as we said to Jan, we have a European project starting. There will be, I would say, similar development. I would be there. How much open is the system for collaboration? Because I hear that your project is now on the end. So how would you disseminate the system? How can we interact with you? If I guess we will have similar question with kind of different constraints, maybe a question of scalability and so on. So how can we interact with you in our new project?
Well, it is very simple. Everything is open source. There's the website, and the website provides links to the GitHub where most of these source code are stored. We have lots of tutorials, material dissemination, and videos, instructional videos. So, I mean, I'll be more than happy to collaborate if you have any questions, of course.